One of the jconf.dev organizers chose this color polo shirt for the Java Champions. So if you can hardly see me, this is why. It's his fault. Thanks, Vincent. Dynamic proxies were added to the language in Java 1.3, which is over 20 years ago, to solve a problem that we had, which was whenever we used infrastructure code like RMI, similar type of things, we would have to go through a separate build process to generate stubs and skeletons so that we could access the remote objects. And this was a bit of a pain because if we forgot to call RMIC after changing the interface, then things wouldn't really work very well together. So Java 1.3, they added the single dynamic proxies, which allows you to create new objects of new classes that implement certain interfaces on the fly. And this made the whole infrastructure code much easier to do. And we can use them in our own code as well. With dynamic proxies, you've got a single invocation handler, which is called when any proxy method is called. So you can reduce the amount of code quite substantially that you have to write and maintain. In the biggest example, we took 600,000 code statement and replaced that with a single dynamic proxy. So it's a huge, huge win. And the code had not been written by hand. It had been generated, but after it was generated, then it had to be maintained by hand. Dynamic proxies are used a lot in different types of infrastructure code. You'll have it in Spring, annotations, dependency injection, Hibernate, Gradle. So we did a search through that, and it's used in lots of different places. And I've even written a book about it. So here's a book. You can get that for free from infoq.com/minibox/Java dynamic proxies. Before I show you how we can dynamically create proxies, I'm first going to show you how to not do it, how to do it by hand. The example I'm going to use is that of the virtual proxy. Now there are different forms of proxies. If you don't know what the design pattern proxy is, I suggest you look it up. But there are different types of proxies. One of them is a virtual proxy where you create something on demand. And if you look at my office here, my desk has got a virtual tidy up proxy. And when I get visitors, I tidy up. And if I don't get visitors, I don't tidy up. So I sort of delay the tidying up until it's absolutely necessary. And my wife says, our visitors are coming tomorrow. They're going to see your office, and then I tidy up. So I'm delaying an expensive object creation, tidying up my office, until the absolute last moment where I can get away with it. And it's always possible if the visitors say, we can't make it, in which case I can wait for the next visitor to arrive, and then only tidy up my office. So the idea with the virtual proxy is to delay expensive object creation until you absolutely need it on demand. This is similar to the map interface. This has 6 methods: size, get, put, remove, clear, and for each. The custom hash map implements custom map and delegates to a normal Java util hash map. So all 6 methods are delegated. I'm also in the constructor printing out custom hash map constructed, just so that we can see at what point it gets constructed. This code can be almost entirely generated by your IDE. And it continues, remove, clear, for each, to string. Now this is of course repetitive and error prone because, well, if you do it by hand, it's error prone. If the IDE does it, maybe it's not as error prone as if you do it by hand, but still it's a pain. It's a pain to do coding like that. We'll get back to that in a moment. Now, we also are going to do a virtual custom map. This is a virtual proxy which creates the real custom map when it's used for the first time. So when I construct a virtual custom map, I pass in a supplier, and the supplier is used to create a custom map. So I pass in a supplier that's stored inside a final field, and then I also pass in a real map. And the real map, I don't pass in a real map. I have a real map field, and the real map field is set inside the get real map method. And the get real map method is a private method that, if the real map is set to null, it creates it on demand the first time you call it. So I've got my 6 methods here: size, get, put, remove, clear for each. Each of them now delegate to the getRealMap method, and the getRealMap will be will set the map the first time that I call it, and then create it. This is what the client code could look like. I would make a virtual custom map, passing in a custom hash map constructor as a method reference, and then as soon as I start using it, you're going to see in the output that the custom hash map was created. So you see exactly at which point it gets created. And after that, it's available, and we can use it. And if we ever use it, then it also doesn't cost us anything. So that's one of the beauties of this pattern, is expensive objects don't have to be constructed up front. We can do it only once we absolutely need it. Like Heinz tidying up his office only has to happen when I've got visitors. If I don't have visitors, well, then it doesn't matter, in my opinion. Nobody can see my mess, so I'll leave it like it is until a visitor comes. And at the current time with coronavirus, visitors are scarce, so my office is getting worse and worse, and big mountains of cables and devices lying on my desk. You can probably relate to that. Now, we've seen how to do it by hand. Let's see how we can do this with a dynamic proxy. And we want to avoid as much as possible either copy and post programming, because when you make a mistake, it gets copied everywhere. Secondly, we also want to avoid generating code with the IDE, because well, you still have to maintain the code by hand. And if you make a change, you've got to change multiple places, and that's another problem with that type of coding. So a better approach is to either do static or dynamic code generation, and we're going to focus on the dynamic code generation. The method we call is proxy.newProxyInstance. And what this does is it takes 3 parameters. First of all, the class loader, where the new proxy class is going to be loaded into once it's created. Then an array containing all the interfaces that our proxy must implement. And then lastly, an invocation handler that is called when a proxy method is invoked. So these 3. And we'll talk a bit more about the different constraints on these different classes. The invocation handler is called when any method is called on the proxy. It takes 3 parameters. The first parameter is the actual proxy object on which the methods were invoked. Then we've got method, which is Java lang reflect method. I'll show you how that gets figured out in a moment. And then the arguments that were sent into that method, and that will be null if your method doesn't take any arguments. You also notice that we return objects, so we can return anything. And the method throws throwable, so we can throw anything as well. But it does have to match, otherwise we get problems later on. For our example, we'll have a look at logging information on method calls. And I'll log. I've got a gift for you. If you go to tinyurl.com/jconf.dev now, like right now, you'll get a gift. If you go there tomorrow, you'll not get a gift. So you have to go there today. All right. So as I wanted to tell you, the logging invocation handler is the invocation handler that's going to be called when any method is called on the proxy object. So, and we're going to optionally measure also the time that each method call takes. So the loggers of, you know what the logger is, it's Java, it's a logger, but then the object is the object on which we must invoke the methods. Here's the invoke method, log.info, information about the method and the parameters, and then if we've got fine level enabled, we're also going to log the time, the nanotime. I've made it optional on and off because nanotime is a fairly expensive method to call, so we don't want to call that unnecessarily. And then we call return method.invoke with the object args, and lastly we measure the time at the end and print out also the time, and the exiting of the method. So you see all this information. There is a mistake in this code, and I've left it in there deliberately. And if you can spot the mistake, good for you. If you can't, well, you'll have to wait. But there's a mistake. Right. So here you've got your toString method, and the toString method is just there to format the method nicely. You can see the method class and the class of the method and the method itself, and the arguments that get passed in. Here's how we could use it. We could say proxy.new proxy instance, and for the class loader has to be able to see the interface which we're going to be proxying. So if I'm using map, javaUtil map, I can use maps class loader. If I'm using one of my own interfaces, I need to use my own class loader. I can't use the Bootstrap class loader to load the class. Then I pass in the logging invocation handler as well, and I'm going to log a concurrent hash map. So then when I call methods like put, you'll see entering and the time and exiting, and there we go. In order to see how this works, it helps to create a dynamic proxy and look at the generated code. And we can do that by taking another interface, isodate parser. And what this isodate parser does, it takes a string and it returns a local date, a javaUtil time, Java time API local date, and that throws parse exception. So if it can't parse it, it throws a parse exception. And that's a checked exception. Now, when I create a proxy with proxy.new proxy instance, because it's my own interface, I can't use the Bootstrap class loader. So typically what I do is I use the same class loader as the interface that I'm trying to proxy. So it's the isodate parser's class loader. And the invocation handler just returns null, so if you call any method, it's going to not really work very well. But what I want to see with this class, or with this object, is what is the actual class, the get class. And you can see, for example, it could be com.sun.proxy.$proxy0. It doesn't have to be, but it's normally following something like that as a pattern. $proxy0, something $proxy0. It's like an anonymous class. And we can actually dump these to the file system when we run our code. So if you want to know whether your system is using dynamic proxies, you can just dump all the generated proxies. You can look at them and see exactly what has been proxied. And so here are the settings for Java 9 and earlier versions on how to save the generated files. And then we can decompile them with a tool like CFR. That's my favorite at the moment for decompiling Java classes. And this is what is generated. It's a public final class $proxy0. So it's final. We cannot extend it further. It extends proxy, which means it's a class that extends the Java lang reflect proxy, and therefore we can't extend other classes because Java does not support multiple class inheritance. Because it doesn't support multiple class inheritance, we also cannot support, we cannot proxy class, we can only proxy interfaces. And it implements isodate parser. So it is an isodate parser as well. Then it contains 4 method fields, and the method fields are Java lang reflect method, M0, M1, M2, M3. And it then it finds the methods for these classes. I think inside internally it actually does class.forename, but with the current class load, I guess. And then, but I just decided to make it easier to show on the slide, I'm saying object.class.getMethod hashcode, and object.class.getMethod equals comma object.class, and then string without parameters, and parse, which takes a string parameter. And If any of those methods doesn't exist, we throw no such method error. So this is part of when the class is loaded for the first time, these method fields are discovered and stored inside the $proxy0. And then we see the constructor, which takes an invocation handler as a parameter and just passes it up to the superclass. And we can access it directly from inside $proxy0. And then here's the hashcode function. The hashcode calls h, which is our invocation handler, dot invoke this, which is the current proxy, comma the method m0, comma, because there are no parameters for hashcode, we pass null up to the invocation handler, but we cast it an object array so that it's clear what that is. Otherwise, you might think it's actually a null argument that's being passed, but no, it's an object array of null. And if a runtime exception occurs or an error occurs, we simply rethrow those. If any other exception occurs, then we have to wrap that with an undeclared throwable exception. And therein lies the problem with the logging invocation handler, because what could happen is an invocation target exception, and in that case we actually would rather throw the cause than the actual invocation target exception. Right, we'll get back to that in a moment. Then equals looks almost the same as hashcode, except that we are also passing the parameter O to the invocation handler, and that is being wrapped as an object array. That object array might be eliminated, but not necessarily. Then we've got the toString method, which is almost exactly the same as hashcode, so I'll skip that, and the parse method, which takes the string and returns a local date. Again, you have to cast the result to local date because h.invoke returns an object. And then the other little difference is that this method declares that it throws parse exception. So we'll catch that together with runtime exception and error and simply rethrow it. And anything else, we're going to throw them as undeclared throwable exceptions. All the methods are final. The class itself is final. We cannot extend it further. Let's see how we can create our own virtual dynamic proxy using this technique. So here's our virtual proxy handler. And the virtual proxy handler is an invocation handler, and I've also made it serializable. I'm not sure how this is going to be used, so rather safe than sorry. Proxy objects themselves are already serializable, but the invocation handlers also have to be serializable. And I've got a supplier inside, I've got a subject inside, and the get subject method, similarly to the handwritten proxy, the handwritten virtual proxy, is going to construct the actual subject on demand when we call any method for the first time. So it says if subject is null, then set subject equal to supplier.get, and then return the subject. And then inside the invoke, this gets called when any method is called on the interface, or hashcode equals and toString, as we saw in the previous section. And so in that case, we simply say method.invoke on the subject, the get subject, which will lazily create the actual subject, comma, the arguments. And I've got a class called Proxies inside my book, described in there. So get the book if you haven't got it yet, and you'll see more information there. And the virtual proxy method calls cast proxy, which passes in, we pass an interface and a virtual proxy handler. And the cast proxy does three different things. The first is very obvious. It does a cast. It casts to the correct type. The second one is a bit more subtle. It also will unwrap an invocation target exception and throw the cause. So if you're doing any reflection, it would unwrap the invocation target exception, pass the cause, throw the cause rather than the invocation target exception. And the third thing it does is it speeds up the method calls. Instead of handwriting our custom hashmap virtual proxy, we can instead just say proxies.virtual proxy, passing in the interface, which is custom map, and the supplier of the custom hashmap, which would just be custom hashmap : new method reference. And the rest of the code is exactly the same. So this is great, a lot less code and less chance of bugs. The less code you've got, the less opportunity you have for making mistakes. And everything works exactly like it did before. Dynamic proxies have some restrictions. For example, you can only proxy interfaces. We saw already that our proxy class extends Java-Lang reflect proxy. There's no multiple class inheritance in Java, so we can't proxy classes. If you need to do that, you need to use another library like cglib or ByteBuddy. But I personally don't like using those tools in production code. I don't mind for test code, but I don't like using it for production code. Then, as I mentioned to you, the undeclared throwable exception. The invocation target throws throwable, but if we throw an exception which wasn't declared as part of the method signature, then it's going to rethrow an undeclared throwable exception. For example, here inside my runnable dynamic proxy, I'm throwing a bad exception, an IO exception. Now, of course, runnable doesn't expect to be throwing an IO exception, so what comes back is an undeclared throwable exception that contains an IO exception. So this is something to be aware of. If you get the wrong exception, if you throw the wrong exception, you're going to have a bit of an issue there. Also, the return types need to match the method signature. So if I've got void, I can return anything, but if it's a primitive, it has to be that type. It can't be null. And if it's not a primitive, it has to be the correct type, because there's going to be some casting happening inside the proxy class, and that's going to give a class cast exception if it's wrong. These proxies are called potentially billions of times because it's part of infrastructure code, and so it's important that it's quite fast. And there's a few places where performance might suffer. First of all, with primitive types being boxed, both as parameters and as return values. Secondly, parameter lists might have to be wrapped with object arrays. In some cases, these can be eliminated as part of your escape analysis, but not always. If they somehow escape from the method, or if escape analysis cannot determine precisely that it can eliminate it, then it's going to still have the allocation cost. The third thing is that when you call a method via reflection, it always has to check whether you've got the permission to do that. It's like you call it and it says, who are you? And they go, well, I'm Heinz. Oh, okay, yeah, you can call the method. And then you call it again and it says, excuse me, who are you? And you say, I'm Heinz. And they go, oh, okay, sorry, yeah, okay, you can call it. And then you call it a third time and it says, who are you? And you go, like, come on, seriously? You know, this is some mental decline inside the method. So it's horrible. However, if you set accessible true on the method, then after that it won't ask again. It'll just say, okay, fine, just go through. Because the methods are all public anyway, it really shouldn't make a difference setting them to be accessible. And so we do that as a way to speed things up a bit, and it does make a difference. Our benchmark is going to have two very simple methods: incrementing along, and consume CPU, which is just going to do, black hole dot consume CPU 2. So it's very, very little work. And the reason I do such little work is because the way we've done the dynamic proxies or the infrastructure code here, it's quite efficient. So if I'm doing any more work, we won't really be able to measure the difference between dynamic proxies and not using dynamic proxies. It's really fast, as we'll see in a moment. Here's analysis of the increment method. And if I call it directly, it takes about 2.9 nanoseconds per operation. Now, this is running on my 162 MacBook Pro, but I turned off the CPU turbo boost so that it's always running at sort of the, I think it's 2.4 gigahertz or something, 2.5 gigahertz. So it doesn't wave up and down. Normally what happens is that your CPU will be clocked up if it has a lot of work, but if it gets too hot, it'll get clocked down again. So heat and workload has a big impact on performance results. And it's just very hard to get consistent results that way. Also, what I did was I chose the best results, not the average results. And so these gave me the most accurate results. So the direct call was 2.9 nanoseconds. The static proxy was 3.5. That's the handwritten one. Then the dynamic proxy direct call. Here I'm cheating a little bit because I am using dynamic proxies, but what I'm doing is I'm not using reflection to call the actual method. I'm just calling the correct method directly, and the code's not actually correct, but it's fast, as you can see. Then the dynamic proxy reflective call with the methods being turbo boosted. That means I've set accessible true on the methods, and 9.7 nanoseconds versus the static proxy, which is 3.5. So that's the comparison we need to do between those two. And if you don't have the turbo boosting on, the method turbo boosting, then it's another 2.3 nanoseconds slower. Now, if you look at the results in the rightmost column, you'll see that for the direct call, no bytes are generated. Also not for the static proxy, because it's just a primitive, so why should that allocate memory? And there are no parameters, so it shouldn't allocate any memory. However, for the dynamic proxy reflective call, it allocates 24 bytes on each method call. And it doesn't matter if escape analysis is on or off, it always allocates 24 bytes. And this object allocation is going to have an impact on our performance. Can't get away from that. Then the consume CPU, we can see the direct call 4.8, static proxy 5.5, dynamic proxy direct call just a bit more 6.6, and then the dynamic proxy reflective call 7.6. And if you want to compare anything, you want to compare the dynamic proxy reflective call turbo versus static proxy. And you can see there's like a 2.1 nanosecond performance degradation per call. The differences are smaller here because I'm not allocating any objects. Because there's no object allocation, I don't have any cost in addition to just the CPU that I'm running over here. And here you can also see a larger difference between the turbo on and turbo off. I'm talking about the method turbo boost, not the CPU turbo boost. That's always off with this experiment. So that's our summary, is 6.2 nanoseconds for increment and 2.1 for consume CPU. And these overheads are going to be most of the time negligible in your typical business application. If I do a database call, if I've got a few 2 nanosecond delays in there or overhead, that's hardly going to be noticeable. A lot of other things are going to be far more expensive than that. So if you have a situation where that is a problem in some really high performance microservice, you probably want to use static code generation. The proxy has a very similar structure to some other patterns like decorator/filter, object adapter, and composite. And so in my book, I used the same mechanism from the proxy in order to, for the dynamic proxy, also to create dynamic decorators, adapters, and composites. And I'll show you just one example. Remember when we looked at the custom hash map, it was, we started with this interface of just custom map with these 6 methods, and then we went and made the custom hash map, and we had lots of repetition. We kept on calling map.size and map.get, map.put, and map.clear, and all of that. And it's a lot of tedious code. And instead, we can also create a filter, proxies.filter. And we pass in the interface called custom map.class and an implementation class like new hash map. And if we want to create lazily this filter, then we can do it by saying proxy.virtualProxy with custom map.class and then proxy.filter and custom map.class and the hash map. And if you also want thread safety, there's another one I've written called synchronized proxy. So lots of different options of how we can wrap the custom map classes. There's a lot more information in the book, and make sure that you don't forget to get the gift, because if you don't get it now, it won't be available. And it's only for you, no one else, only those of you listening right now. Please get it. I've also got a free Java Specialist newsletter, which you're welcome to subscribe to. And if you want to say hello, Heinz at javaspecialists.eu, always happy to hear from you. And I think now I've got time for questions. Hope you enjoyed this.